Speeding at C, it's me, Z, and welcome to the second video of Z's PDEs, the wave equation. Now, this is a super special video because we're diving into our very first PDE. We're going to be going over examples, the derivation, and maybe even get to see some cool animations. But before we get started, I wanted to thank you all so much for the support during the past 2 videos. Reading the comments, seeing your guys' questions on the Discord, and more have really kept my spirits up, and I'm so excited to show you guys what's next for this series. So, if you have any questions, feel free to put them in the comments below, and let's get started! Let's just start right off the bat. The wave equation is d squared u dt squared is equal to c squared times d squared u dx squared. And this is defined over a range of 0 to x to L. So x goes from 0 to L. And time is greater than 0. We're also given boundary conditions and initial conditions. Boundary conditions say that at position x is equal to 0, the solution to the wave equation u should also be 0. At position x is equal to L, the solution to the wave equation, which is u, should be equal to 0 as well. These are also known as Dirichlet boundary conditions. And later in this video, I'll also go and explain what these different types of boundary conditions are. But this is the most simple case. We're also given initial conditions. Ux of 0 is equal to f of x, and du dt x of 0 is equal to g of x. What this means is that at the very start, when time is equal to 0, f of x describes the shape of the wave at the start. Similarly, at time is equal to 0, g of x describes the change in the wave at the start. And this little triangle symbol I drew here was delta, so the change in the wave. With these, we need to ask, what is the solution to the wave equation given these conditions? In order for us to solve for the wave equation, we need to use a method called separating variables. That means we're taking the original differential equation that I showed in the previous slide and decomposing it into parts that we can actually understand. So step 1 is to separate variables. So what does this mean? We know that our solution, which is of the form u, tx, so time and position, is of the form x of x, t of t. That means that there is one component that is solely made up of position and one component that is solely made up of time. And what we need to do is plug in this format solution into the wave equation. So you might be wondering, how do you do that? There's a ton of differentials here. This looks like it's just a product. How do you combine these two together? Well, the way that you do that is by actually conducting the derivative on this separated format. And by doing that, we get, for instance, d squared u dt squared of u would be equal to d squared dt squared of x of x and t of t. But note that this derivative is only with respect to time, which means that this is like a constant. It doesn't have an impact from the derivative. Whereas this is actually influenced by the derivative. So this can be simplified into x times t double prime. And I'm just getting rid of the parentheses here just to make it look a little nicer. And if we were to repeat that for both sides of the equation, we would get x t double prime is equal to c squared. It's a constant, so it stays the same. And this is a double derivative of x. So we only implement it on the x term of the solution to the wave equation. Now what we have to do is we have to solve for what x and t are. And to do that, we actually have to move the variables to the same side of their equation. So we move the x terms, we move the y terms, the t terms. And what we get is this expression here, x double prime over x is equal to t double prime over c squared t. But what we do know is that this is equal to k. That can just be any number. We're setting this as an arbitrary separation constant. And this is important because we'll later solve for what this separation constant is. And then in the meantime, we can take our two equations here and transform them into equations with respect with k. So by separating the variables, we now have these two equations. And these might look really nice to you because they're basically ODEs. So we took a PDE and we separated it into two ODEs that is much easier to solve. Step 2 is to solve for these separated equations. So you might be wondering, how do you solve for these? We don't even know what k is. Well, we know that k can be one of three options. It can be either positive, negative, or 0. And we consider each of those different options. So let's start with the first separate equation. X double prime minus kx is equal to 0. In this case, k is positive. That means that we can describe k with respect to another variable. Let's say it's mu squared. The reason why I'm squaring this arbitrary number is because when you square a number, it will always be positive. So this guarantees that k is always positive. And we plug that into this expression here. So we get x double prime minus mu squared x is equal to 0. And just like we did in the ODEs video, if you haven't already, go check that out. You solve for the characteristic polynomial. So you get lambda is equal to plus or minus mu. So f of x is equal to c1 e to the mu x plus c2 e to the negative mu x. And that's from solving the characteristic polynomial. This is basically just solving out an ODE. Now this is great, but how do we know that k is positive? Well, what we have to do is apply the boundary conditions. At the start, I said that u of 0t is equal to 0 and u of L of t is equal to 0. This is important because these are only dependent on x. So we can actually translate this into x of 0. So the solution to the wave equation at position x is equal to 0 is 0. And x of L is equal to 0. And what we do is now we plug that into this equation and see what we get. So let's first start with x of 0. When we plug this into x, c1 e to the 0 plus c2 e to the 0, we get c1 plus c2 is equal to 0. That means that c1 is equal to negative c2. Similarly, now that we know that c1 is equal to negative c2, we can plug that into our second boundary condition, which says that x of L is equal to 0. So we start out by saying c1 e to the negative mu L plus c2 e to the mu L is equal to 0. But now we can plug in for c2 and take that out. And we get that c1 is equal to 0. But because c1 is equal to negative c2, c2 is equal to 0. What? Does that mean that our position function is just 0? Well, that means we did something wrong. And that is that our assumption was incorrect. K cannot be positive. So let's try our next case, that k is 0. To do that, let's start with our separated function again and plug in k is equal to 0. Then we get x double prime is equal to 0. So if we solve for the characteristic polynomial, lambda is equal to 0. We then get that x of x is of the form c1x plus c2. And again, let's plug in the boundary conditions. So we know that x of 0 is equal to 0. We plug that in. So we're getting c2 is equal to 0. That's a little sus. And we're getting that x of L is equal to c1 L plus 0 is equal to 0. So c1 is equal to 0. Uh-oh. This means that we got c1 and c2 equal to 0 again. So that means that assumption must not be right. So now we're down to our last option. K is negative. Now don't worry, because this actually ends up in a good ending. This means that we can turn K into negative mu squared. Mu squared turns everything positive. So sticking a negative sign in front of it means that K must be negative. So this is our separated equation now, plugging that in for K. And again, we solve for the characteristic polynomial. And we get an imaginary solution. But don't worry, we had a ODE solution for that as well. So x of x is equal to c1 e to the 0, because there is no real component here, times cosine mu x, because the mu is right in front of the imaginary number here, plus c2 e to the 0 times sine of mu x. Now we just have to plug in the boundary conditions again. So x of 0 is equal to 0. So let's try plugging in x. So we get c1 cosine 0, which means that c1 is equal to 0. Uh-oh, does that mean we're going to get another 0 case? Nuh-uh. We have to check the second boundary condition. X of L is equal to 0. We can say that this is equal to c1 cosine mu L plus c2 sine mu L from the equation above. But we know that c1 is equal to 0, so we can cross that out, which means that c2 sine mu L is equal to 0. But here's a little handy shortcut. Let's take a look at the sine function. We're saying that this equation looks a little bit like this sinusoidal function here. And you might notice that there are two zeros. So there's one at 0 and one at x is equal to L, which represent our boundary conditions. But there's another 0 that's here. What we can actually do is this handy little trick where we set mu is equal to n pi of L. That's because sine of n pi must always equal to 0. And that's because every time the sine function swoops down, we're accounting for that fact in how we derived mu. So C2 is not equal to 0. And in fact, what we can do is say that mu is equal to n pi L, and therefore, because k is equal to negative mu squared, we say that k is equal to negative n pi over L squared. And putting this all together, we get x of x is of the form sine n pi L x. And there is the constant C2 here, but we're actually going to combine it with our next equation. So for now, we can just leave it like this and say, this is the solution for 1/2 of the separated equation for the solution to the wave equation. Now, don't forget, we also need to solve for t, time, because again, our solution is of the form x of x, t of t. We just did the x component. Now we need to do the t component. So just to recap, we got that our separate equation for time was t double prime minus k c squared t is equal to 0. But now we know that k is equal to negative mu squared and mu is equal to n pi over L. That means we can plug that into here without having to do all of that solving and guessing and checking again. So now we have the expression t double prime plus c times n pi over L squared t is equal to 0. We solve for this again with the characteristic polynomial. So lambda squared plus c times n pi over L squared is equal to 0. And that means we get that lambda is imaginary once again. But again, we also know how to solve this ODE. By separating it out into its trigonometric terms, we get the solution for time. Now here, I'm putting the constants bn and c of n. And the reason for that is because later, when we get a general solution, we'll have to take the summation over the position and time terms. I'll explain a little bit more about that in a second, but these constants will later be dependent on n in a way that we'll later solve for. But so far, This is the other half of the equation we need for the solution to the wave equation. So now finally, we can combine this into one solution. U of xt is equal to x of x times t of t, and we solve for each of these different parts. And so by putting these parts together, we have the sine component from the position and this cosine-sine mixture from the time. But we can't forget one thing. We actually need to take the summation over all n. And the reason for that is because our general solution is dependent on the coefficients b of n, c of n, which then further depend on n. The reason why we are summing over n is because of this special property known as superposition. I delved a little bit into it in a previous video, but it basically states that the combination, the summing of different solutions together is also a solution to the partial differential equation. And so by summing over n, we account for all of those solutions in this general solution. Okay, great. So we just got the general solution. But what is b of n and c of n? Well, we actually have to solve for those coefficients next. But here's a hint. We gotta use our handy dandy Fourier series, which is why I covered it in the previous video. Let's say that we have certain initial conditions. When we are given initial conditions, we can actually solve for the coefficients b of n and c of n. So let's plug in t is equal to 0. We then know that u of 0x would then be the summation b of n times sine m pi x over L. That's because the cosine that was previously in front of the b of n has now gone to 1. Because before it was cosine m pi c L times t, and this goes to 1. And we still have kept this term, which is dependent on x and has no dependency on time. But what if we say that instead of knowing the wave's position, or u of 0x, we actually know the change in the wave's position, which we can say du dt 0x. Well, then we can again solve for the derivative. So we take the derivative of the solution above and we plug in t is equal to 0. And by doing that, we get m pi c over L times c of n sine times m pi x over L. Now here's a really cool trick. This b of n here is only being multiplied by a sine equation. This c of n here, excluding this constant term, is only being multiplied by this sine equation. That is actually an indicator that we need to use the Fourier series. We can actually write b of n is equal to 2 over L, 0 to L, u of 0x, sine m pi x over L dx. So you might be wondering, how in the heck did Z get this crazy equation just by looking at that? Well, it's basically just taking these three parts and swapping them around. We have u of 0x here on the left side. We need to solve for b of n, and we have this sine series here. And by taking this, we can actually interpret that as the function that we want to decompose into its sine components, and how much of each coefficient needs to be added up together to build that u of 0x. So, because this is on the left-hand side, what we're trying to solve for, we plug it in here. We know we need to solve for b of n, and that actually moves to the left-hand side here where it's now isolated. And we're using the sine Fourier series, so we multiply by sine times m pi x over L. And because of normalization, we also need the 2 over L term here. We can repeat the same analogy for c of n, except this time notice that this coefficient in the front is a little bit different. That's because we have this little constant term here that we need to account for. So we put this c m pi into the denominator here. and we have to multiply by L, which cancels out the L on the top and bottom. So the coefficient in front is 2 over Cm pi. Again, we know that this time we need to solve for du dt 0x. So we plug that in to the Fourier series here. We are using the sine Fourier series, so that also goes there into the integral. And we are solving for the coefficient C of n, so that goes here on the left-hand side. And so by using the Fourier series, we were able to take this crazy looking expression and actually isolate the coefficients just by using the initial conditions. So that was a lot of math being thrown at you. So let's go through an example. This is the plucked string example. What we have here is a little picture of the string at t equals 0. We are holding the string right at the center. And fortunately, we have a little equation to help describe that, which is negative x minus L over 2 squared plus L squared over 4. It's like half of a circle. And we're saying that is u of 0x. We're also given that there is no change in the wave at the start, which makes things a little bit easier. That means that we're holding the string at rest and then seeing what happens when we release it, which is when time starts. Now that we're given this, we know that because the change in the wave at the start is 0, we know that C of n is equal to 0, which means we only need to solve for B of n. So how do we do that? We need to use our handy dandy little Fourier series. We know that B of n is equal to 2 over L times the integral of 0 to pi times u of 0x times sine of m pi x over L dx. And now we just need to plug in the expression of us holding the string. It's as simple as that. So we're going to put this right here. All right, so we got this crazy integral here. And of course, I could probably sit here and go over for the next like 10 minutes how to solve this. But thankfully, we have things like integral calculator and Wolfram Alpha. And after plugging that in, we get this crazy expression here. But don't worry, this is basically just a constant explaining what B of n is. And so if you were asked, what is the solution to the wave equation? How does this system evolve over time? When we release a string, what does the wave look like at t is equal to a specific time? Well, all we need to do left is to plug this in to our solution. So here is the original solution to the wave equation given the specific boundary conditions. Now, this is not as important for this question, but the reason why I say this is for specific boundary conditions is because in this example, the position of the string at position 0 and position L is bounded to 0. There might be cases where that is not the case, which we'll see in a future video. But right now we have this expression. We know that C of n is equal to 0, so we can basically get rid of this term here. And all we have to do now is plug in B of n. Which means that our final solution is this hefty equation, which is the summation of n for sine times m pi over L times x, which is the position part of this expression. And this right here is the time part of the expression where we plugged in this constant, which is dependent on n, which is important because we're summing over n. And we have this sinusoidal time component here. Now you might look at this and be totally unconvinced that this is the correct answer, but I actually took the duty of simulating this and showing what the string looks like as it evolves over time. This comes to show that yes, the math looks really crazy, but these can actually be used as really important tools to model physical systems. Alright, so to recap today's video, we started out with the separation of variables, which allowed us to take a crazy looking PDE for the wave equation and separate it into ODEs that are much easier to solve. From that, we were able to get the general solution to the wave equation, which was defined by this summation over here. We then said that if we're given initial conditions, we can actually solve for B of n and C of n with the handy dandy Fourier series. So that was the wave equation. I hope you really enjoyed this video. The wave equation is the first PDE that we actually went through in depth, and I'm super excited to show you guys what's next. Next up is going to be another type of PDE known as the heat equation, and we're going to have a lot of fun dissecting that one too. So, thank you all so much for watching. Again, please be sure to like, subscribe, and comment down below if you have any questions or if you want to see more of this series. I put a lot of love and effort into building this, and I really hope you guys are enjoying it. Thank you all so much for the kind words and for the support during the LA Wildfire fundraiser, which is the only reason this series happened in the first place. So thank you all so much, and I will see you in the next one. Bye bye!